Welcome to the Explainer. Today, we're diving into something genuinely mind-bending. What happens when large language models meet the world of statistical mechanics? It's a brand new paper that has been making serious waves, and we're going to break it all down so you can see exactly why it's such a big deal.
I mean, think about it. What actually happens when AI attention mechanisms start borrowing the math of quantum physics? It sounds kind of like sci-fi, right? Well, it's not. This is a very real, highly technical, cross-disciplinary breakthrough. It fundamentally rethinks how modern sequence models, the engines behind today's AI, process context. And by the end of this explainer, you're going to understand exactly how it works.
Okay, let's dive right into this. We've got a clear path today. First up, the softmax bottleneck. Then we'll enter Boltzmann attention, explore the quantum twist, go over a developer guide, and finally show you how to search arXiv to find the paper yourself.
Part 1. The softmax bottleneck, AI's zero-sum game.
So, to appreciate the cure, we really need to understand the disease. Right now, standard transformers hit a wall with something called softmax normalization. Think of the attention mechanism like a pie. Softmax forces a strict probability distribution, meaning it is a zero-sum game. If one token grabs a bigger slice of that pie, the other slices literally have to shrink. It's great for local focus, sure, but it completely blocks true, explicit coordination between different positions in a sequence.
And this brings us to a major issue. What happens when your AI needs to do some heavy lifting? Things like bracket matching or really long context reasoning. Because of that softmax bottleneck, standard models basically have to fake it. They rely on deep, super expensive layer stacking just to implicitly guess at these relationships. As you can imagine, when sequences get longer, this becomes incredibly unstable and scales, well, terribly.
Which leads us to Part 2. Enter Boltzmann attention, explicit coordination.
This is the physics-inspired solution introduced in arXiv paper 2606-12478. So, what exactly is Boltzmann attention? It's an energy-based generalization that just throws out softmax normalization entirely. Instead, it uses an interacting Ising model from statistical mechanics. Picture magnetic atoms snapping into alignment. Let's swap our pie analogy for a team analogy. Instead of fighting over slices, tokens act like a cohesive team. They explicitly cooperate or even mutually suppress each other using learnable pairwise couplings. The coordination logic is baked directly into the layer itself.
And this brilliantly illustrates the shift. On one side, softmax is trapped in implicit competition, a strict zero-sum dynamic relying on deep layer stacking. But on the flip side, Boltzmann attention gives us explicit interposition correlation. Those learnable pairwise couplings mean the model is actively building cooperative structures. It's a massive upgrade in how the architecture handles information.
Now, the underlying math follows the Boltzmann distribution. But don't worry about getting bogged down in the formula. The main takeaway here is this. Instead of forcing a rigid probability curve, the network minimizes energy during backpropagation to find valid attention patterns. It naturally settles into the most stable state.
And you know what? The benchmarks back this up beautifully. Boltzmann acts as a straight-up drop-in replacement for softmax, in vanilla transformers delivering a clear linear scaling advantage as sequence length grows. The researchers even ran a rigorous four-way ablation study. They completely isolated those pairwise couplings, proving they are the sole driver of the performance boost. No regularization artifacts involved. It just flat-out beats implicit layer stacking.
Moving on to Part 3, the quantum twist, sampling the energy. Since we're using an energy-based model, attention weights are sampled stochastically, not deterministically. You need a way to sample that energy. And here is the twist: diabetic quantum annealing. It's basically slowly cooling a complex quantum system until it naturally finds the perfect answer. This gives us a highly stable, viable sampling pathway during training, keeping performance competitive while opening the door to actual quantum computing strategies in AI.
Now, what's really interesting about this is the sheer scope of the breakthrough. Look at the official cross-listings for this paper: machine learning, statistical mechanics, and quantum physics. We are literally watching advanced computer science collide with fundamental physics to solve the next era of AI scaling.
All right, Part 4, the Developer Implementation Guide.
Let's bring this theoretical physics back down to earth for the developers tuning in right now. The magic number to remember here is 512. That's your token sequence threshold. Below 512 tokens, softmax is actually still more efficient because it has a lower parameter overhead. But the second you push past 512, the gains from Boltzmann's explicit coordination become extremely clear and measurable.
There is a catch, though.
and it's big O of n squared. You've got to keep in mind that these pairwise couplings add a quadratic memory overhead relative to your sequence length, meaning if your sequence doubles, your memory requirement goes up by a factor of 4. So definitely something to plan for.
So here is your quick implementation checklist. Integration is a breeze. It's a drop-in replacement where you just swap the attention module and pass the couplings to the optimizer. For memory footprint, you absolutely need to enable gradient checkpointing or use sparse coupling masks to avoid maxing out your VRAM past 1K tokens. For stochastic training, use warm-up schedules and lower initial learning rates to handle early gradient noise. And for the quantum pipeline, use quantum annealing for training, sure, but stick to exact classical Boltzmann sampling for inference and production.
Finally, Part 5. Searching arXiv for more.
I highly recommend checking this out yourself. The brilliant minds behind this paper are Gilhan Kim and Daniel K. Park. Those are the specific names you'll want to look for.
Let's move to the search bar and see how this builds. When using arXiv's advanced search, enter Kim G, Park D in the authors field. That semicolon is key for multiple authors. Next, pick all fields for the subcategory so you don't miss the cross-listed physics tags. And finally, sort by submission date to guarantee you're getting the absolute latest version.
So what does this all mean? It leaves us with a truly provocative question. If energy-based attention can successfully merge with quantum sampling to fix AI's context bottleneck today, what discrete latent variable models will this unlock tomorrow? Could this be the bridge to entirely new structure generation pipelines? The foundation is officially laid. Thanks for joining me for this explainer. Keep learning, and I'll catch you next time.